Спасибо. Okay, so last time we proved that zeta function over a hypersurface is an meromorphic function. T, so z of t equals the ratio of a of t and b of t for certain power series entire functions. So they converge in the whole plane. Okay, so this was the key result, and just from this, today we will deduce the desired rationality property. Okay, and this deduction is purely formal. It uses no p-adic analysis whatsoever. So today is probably the most elementary class of all. Namely, we will prove some classical lemma, probably going back to Kronecker or even before Kronecker, I'm not sure. So it says that given a function f of t, like this, and as I said, the nature of coefficients is irrelevant today. So ai are in some field of arbitrary nature. So given this, we consider a Hankel matrix, capital A, like this. So it's A0, A1, A1, A2, 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 and so on. So it's an infinite matrix. And we set ASM is a certain submatrix, truncation. So it's A S plus I plus J for 0 less than or equal to I, J less than or equal to M. So it's M by M, well, M plus 1 by M plus 1 matrix starting at some point here. And NSM is the determinant of this truncated matrix. And the claim is that our function is rational. If and only if there are certain integers m and capital S, such that for any s bigger than this one, and Sm is 0. So the big enough minors of this matrix vanish, and this guarantees that this power series is the expansion of some rational function. And we will prove this. So in one direction, it's almost immediate if f of t is rational. Say yes. Pardon me? Absolutely, yeah. Why? Yes, yes, right. Mm-hmm. 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 Yes, you're essentially right, but so, well, maybe let me still explain it in one direction where it is really nothing special. And then we'll see in the opposite direction is essentially what you say, but you need some care to, well, to write down this recursive relation. Well, it is essentially evident I don't. It could be given as an exercise, but maybe I wouldn't be able to solve this exercise, so I'd rather. Uh-huh. Mm-hmm. Well. No, certainly I'm going to prove it, yeah, if you don't mind. So this is a degree M polynomial, bi t to the I, and q of t equals, maybe let's be capital M. For capital N degree, like this. Then for I bigger than the maximum of those two degrees, from the relation f of t times q of t equals p of t, we get the collection of linear relations, the sum from j equals 0 to capital N, ai minus n plus j times c n minus j equals 0. Okay, so now take this capital S like this, equal to the maximum of m minus n plus 1 and 1, and take small m equal to capital N. So now for S bigger than capital S, we write down these equations. For I equals S plus capital N, S plus capital N plus 1, and so on, S plus 2n, So the first equation will be AS C capital N plus AS plus 1 C capital N minus 1 plus so on plus AS plus N C0 equals 0. Then the second one will be S plus 1 Cn plus A S plus 2 Cn minus 1 plus so on plus A S plus N plus 1 C0 equals 0 and so on. And finally A S plus capital N Cn plus A plus S plus N plus 1 C N minus 1 plus so on plus A S plus 2N C0 equals 0. Okay, so we know there is a non-trivial solution, and hence the determinant of this matrix must be 0. Okay, so it was in the evident direction, and in the opposite direction, it's a little bit more cumbersome. So if NSM vanishes for all small s, starting from somewhere, take the minimal m, well, like this. And then the lemma, oh, well, this was lemma, so a sublemma. Says that for any s like this, n s m minus 1 will never vanish. So m is the minimal for which all those determinants do vanish, but then no smaller determinants vanish. That's the claim. And this will allow us to prove the lemma, because then we'll be able to say express always the mth say row in each such minor from the previous ones, because the determinant never vanishes. Otherwise, we would not know that the last one is expressible from the others. Maybe it would be something else. Oh, sorry. Yeah. Yes. Thanks. So otherwise, a non-trivial linear combination of the first m rows, say R0 and so on, R m minus 1 of our minor ASM vanishes. Everywhere. I think it's m, yeah. From 0 to m minus 1 is m altogether. So it's vanished everywhere except for the last column. And then let R I naught will be the first row with non-zero coefficient in this linear combination. Why does it? Because we assumed that some determinant like this vanishes.
Okay, but why except for the last column?
Because the last column is, well, this is M minus 1 by M minus 1 matrix. And its rows are linearly dependent. But we extend it to M by M matrix. Or what I'm saying? Yes. Yes. It's M by M, right? The size of ASM is what? It's M plus 1 by M plus 1. Sorry. But anyway, it's the size of 1 bigger. So in this size, we will make sure that our linear combination vanishes. But our matrix is actually one size bigger. So at the border, it might have non-vanishing element. Yes. OK, so we take this particular index, having non-trivial, non-zero coefficient. Pardon me? No, I mean, we assume that this determinant is zero. This means that there is a non-trivial linear relation. In the last column, certainly we also could have 0 as well, yeah. We just don't know what we have. It could be 0 as well, yeah. Vanishes, possibly, except. OK, so let this index I naught will be the first index with non-trivial coefficient in this linear combination. So that R I naught can be expressed through the next rows. Alpha 1 R I naught plus 1 plus alpha 2 R I naught plus 2 plus so on plus alpha M, sorry, minus I naught minus 1 R M minus 1. So we have this equality, again, except possibly in the last column. OK, so replace this row R I naught in the truncated matrix ASM by R I naught minus the right-hand side of this. Then, if I naught is strictly positive, we get the matrix like this. AS plus 1, and so on. AS plus M, AS plus 1, AS plus 2, and so on. AS plus M plus 1. So we proceed like this till the position I naught. And there we have all zeros, except for possibly the last row, where we have something possibly non-zero. And then finally, we have a s plus m, a s plus m plus 1, and so on, a s plus 2m. Okay, and then we consider the following submatrix. So we remove the first row and the last column. And the determinant of the lower left corner is, on the one hand, it is just n s plus 1 m minus 1, just by definition. There's a typical minor. On the other hand, it will have this totally vanishing row, so it'll be equal to 0. Okay, so we started from the assumption n s m minus 1 equals 0. We deduced n s plus 1 m minus 1 equals 0. And then we continue like this. From this, we will deduce n s plus 2 m minus 2 equals 0, and so on. And so m is not the minimal. Number. Because we deduced that, it's m minus 1. Because we deduced that all the minors of size m minus 1 also vanish. We started from just particular one, number s, and we deduced that the next one, s plus 1, vanishes too. But then we just argue like this. We increase s plus 1 to s plus 2, and so on and so on. And so all of them vanish. And so it's a contradiction. Okay. It was if I naught is bigger than 0. Now, if I naught is 0, then we get the following matrix. It's 0, 0, 0, and then possibly some non-zero beta. Then a s plus 1, a s plus 2, and so on. And then a s plus m plus 1. And then so on. And finally, a s plus m, a s plus m plus 1, and so on. And in the end, a s plus 2m. Okay. And again, we have this lower left corner, but no colored chalk. Sorry. Pardon me? I have some colored chalk available. Thank you very much. And why do you have it? Why do you have it?
Я преподаватель.
Aha, I see. Thank you very much. So we also will have upper right corner.
Зачем? Мы же тогда знаем,
Why?
Мы знаем, что АСМ вся ноль, а ее определитель это вот левый нижний
Right,
Остальное происходит точно.
right.
Вот она нижний левый как раз ноль. Все.
So, well, it means that either this determinant is 0 or beta is 0. But if beta is 0, then the right corner is 0. So either the lower left corner has determinant 0, which is n s plus 1, m minus 1, or beta is 0. And then the upper right corner has determinant 0, which is again equal to n s plus 1 m minus 1. Okay, so we are done with sublemma. Yeah, just because the total determinant n s plus 1 m is just this times beta. Okay. So the sublemma is proved. And now maybe let me erase this proof. So this is the statement. Pardon me?
Это не факт. Может быть, экран, может быть, просто экран.
So I can continue in Russian.
Связано, ну ладно.
All right. So am I allowed to speak in Russian? No. No. Well, now sublemma is here and lemma is there. And we can continue the proof of lemma using this sublemma. Okay. Okay. So from this sublemma, we see that there is a vanishing linear combination of rows of this truncated ASM matrix whose last coefficient is non-zero, just because the total determinant NSM is 0, but the any smaller one is not 0. And hence, the last row of ASM is a linear combination of all the rest rows and we can write this down. So we'll see that any solution of the system AS UM plus AS minus 1 S plus 1 UM minus 1 plus so on plus AS plus M U 0 equals 0 and so on. And finally, AS plus M minus 1 UM plus AS plus M UM minus 1 plus so on plus AS plus 2M minus 1 U0 is 0. Any solution of this system is a solution of the next equation, AS plus M U M plus AS plus M minus 1 U M minus 1 plus so on plus AS plus 2M U 0 equals 0. And well, proceeding by induction, it is a solution of any equation whatever T U M plus A T plus 1 U M minus 1 plus so on plus A T plus M U0 equals 0 for any T bigger than capital S. Okay, but this means that the sum of U I T to the I times the sum AI T to the I equals a polynomial of degree less than capital S plus M. Okay, so we're done. And it's, as Kirill said, it's essentially evident, but does need some organization of calculations. Yeah? Does require some discipline of calculations. Where? Here? Maybe I don't care. I could have 100 plus this here. Okay. So now, armed with this very useful algebraic lemma, we are going to prove Dwork's theorem. So we just have to make sure that for zeta function, such determinants do vanish. And the determinants vanish for some trivial reason. Well, just because we know something about convergence, we'll know something about the growth of coefficients ai of the zeta function, and we'll know something about the p order of coefficients of these determinants. Just because we know that the coefficients of zeta functions of zeta function have some certain growth, and also we know that they are integers, those coefficients, and so we'll know some estimate on their Archimedean norm, and those two estimates will be contradictory. I mean, the product of this norm and the Archimedean norm will be less than 1, which is impossible. So let's do this. So by the Weierstrass preparation theorem, if a certain function is an entire function, then for any finite radius, there is a polynomial and a series f naught of t such that f naught and f naught inverse both converge in d of r in our disk, and our function f is the product of p and f naught. So this is just a reminder about the Weierstrass preparation theorem. So set our zeta function to be the ratio of two entire functions. This was the main result of the previous class, and somehow this is the key thing we're using. Nothing else, essentially, we will use. Okay. Now take r equals q to the power 2n, and n was the dimension of our hypersurface. It was n minus 1. So it was hypersurface in n-dimensional affine space. So let's apply the Weierstrass theorem to the ratio to the function b of t. Okay, where g of t converges in our disk, and p of t is a polynomial. Okay, so then f of t, the product a of t times g of t, converges in the same disk. and f of t equals our polynomial p of t times the zeta function. So let's write f of t is the infinite sum of bi t to the I. So it starts from 1. And let's write p of t equals the sum ci t to the I. So e is the degree of this polynomial p of t. Okay. And z of t is the zeta function, the sum of a I t to the I. So we know that it has positive integral coefficients. Okay, so we proved that those coefficients ai are at most q to the power in. And we just proved it by counting, yeah, because our hypersurface lies in the affine space over finite field fq, and we just counted the points in this affine space, and it gave us this estimate. So it was very straightforward. Okay. Since f of t converges in our disk of radius q to the 2n for big enough indices, we have the norm, well, the p-adic norm of bi is at most r to negative I, which is q to the negative 2in. Okay, now fix some m. We're going to apply this key lemma we just proved before. Yeah, so we needed some size of truncated matrix, yeah, and also some point from which on this truncated matrix had vanishing determinant. So we fix m that is bigger than 2e. 2e was twice the degree of our polynomial p, and set sm is this truncated Hankel matrix as before, s plus I plus j of size m plus 1, and nsm is determinant. So we want to prove that this vanishes. Okay. So how do we prove this? We know that f of t equals p of t z of t, and hence b j plus e equals a j plus e plus c1 a j plus e minus 1 plus so on plus ce a j. Okay. So in the matrix, this truncated Hankel matrix ASM, let us add to a column number j plus e well, starting from the last one till the eth one. So we'll have j plus 1 columns like this from right to left. So we add to a column the linear combination yes. Yes, we take a column like this and replace it by a certain linear combination of other columns. Okay, so add the linear combination over E many previous columns. With coefficients C, K, well, let's say of the J plus E minus K column. Yes. Okay. Maybe I shouldn't erase this. But we do have this relation, and I somehow reproduce it for columns of our Hankel matrix. So I take some column, well, this number J plus E, and then I take the previous columns, J plus E minus 1, and so on, and then finally J plus E minus K, and so on. Well, I write like this. Only the column, how should I denote it? Well, let me denote by capital C. C, J plus E, and so on. C, J plus E minus K. But I just add to this one such a combination of the previous ones.
Правда ли, что ты берешь одно J и это делаешь и все? Или ты делаешь это со всеми J?
What, how to say? I fix one J and do this, but also for other J's, I do the same. For all yeah. Just the column. The problem is that I have coefficients small c. Well, maybe let me denote by S, like столбец. Pardon me?
В каком порядке ты это делаешь с разными колонками номер J плюс E?
Just I. Well, I don't know, independently. So I replace S, J plus E by this, by what I said, by S, J plus E. Sorry, maybe. By C1 S J plus E minus 1 plus so on plus C E S J. Okay? Yeah? The only I must edit, sorry. S J plus E plus this. Okay, S J plus E plus this combination. Just what is written here. The same linear combination. Okay? So we obtain a new matrix, say A prime, SM. So its first E columns are the same as for the initial matrix ASM, and the other columns well, are built over B instead of A. Okay, just by this formula. But the determinant of this new matrix is the same as the determinant of the original matrix. But now we can estimate the p order of this determinant. Okay. So we estimate the p order of a determinant of A prime SM. So we know that all ai's are just integers, and hence they have norm less than or equal to 1, and hence the norm of the determinant is at most the maximum of norm of B for J at least S plus E to the power M plus 1 minus E. So our matrix has entries either B or A. For A's, we just need to know that they're integers, nothing else. For B's, we don't yet know. I didn't yet say anything, but we'll have products of not more than BB coefficients like this, and maybe BJ. Now we know that this is at most r to the power negative s m plus 1 minus e for s big enough. Just because we knew that this was true. Okay. So we have r equals q to the power 2n, and m was bigger than 2e, and so it implies that the p-adic norm of NSM is less than q to the power negative n s times m plus 2. Okay. Now we can estimate the Archimedean norm. Over NSM. And this will lead to contradiction. I mean, if you know this, it means that, well, this is we know that this is an integer, right? And this integer is divisible by high power of p from this, right? But on the other hand, we'll momentarily see that this is a comparatively small integer, and it cannot be divisible by such high power of p. And this will be the contradiction. So what do we know? That the NSM Archimedean norm is at most m plus 1 factorial, just the number of summands in the determinant, q to the power n times s plus 2 m times m plus 1, just because we knew that any a was less than, where was, yeah, here, just from here. Yes, thank you. Okay, so this is equal to m plus 1 factorial, q to the power 2n m times m plus 1 times q to the power ns to m plus 1. Okay, so now we can multiply those two inequalities. NSM Archimedean norm times NSM p-adic norm is less than q to negative ns m plus 2 times m plus 1 factorial times q to 2n m plus 1 q to ns m plus 1, and this is m plus 1 factorial q to the 2n m plus 1 over q to the power ns, and this is less than 1 for big enough s. So it's a contradiction unless NSM is equal to 0. That's it. S and M? This one. Yeah, this n is just the dimension of our affine space. Our hypersurface was HF was in AN. So it's fixed once and for all in our argument. This n. And M we also fixed, yeah, namely, where did I fix it? Here. It's bigger than twice the degree of this polynomial p. So that's it. But as I warned you many times, I don't understand this proof. Well, it does have 3 key steps. But none of them I understand. Pardon me? Yeah, because we know that for any integer m, its Archimedean norm times the product of all non-Archimedean norms is 1. Right? But those norms are not more than 1. So if the two of them, well, this and one for a particular p, is less than 1, then we're out already. In other words, small enough in Archimedean norm integer cannot be divisible by high enough power of p. Yes, that's true. That I can appreciate, yeah. So that's it. Thank you. Well, I can say a few words, but we have 15 minutes left, I mean, and I can say a few words about Minkowski-Hasse if you are interested, but I cannot give any proofs. Yes, we'll be glad to. Well, in fact, there are many more interesting things about p-adic numbers. It's just the very 0 level what we covered. And one thing very classical is indeed the Minkowski Hasse principle saying that a quadratic form Q from some, say, rational space, well, to rationals. Well, then I got formulated in various equivalent terms, but for example, has a non-trivial zero. I mean, certainly Q of 0 is 0, but maybe Q of non-zero vector is never 0, like for positive definite quadratic form over real numbers. So it does have a non-trivial 0 if and only if Q tensor R and Q tensor QP does for any P, well, and R. So there is some global problem for algebraic number field, global field Q, and it has a solution if and only if all the local problems do have solution. And the standard counterexample I mean for higher degree equations, is, say, elliptic curve E over Q, given by equation 2y squared minus, well, equals 1 minus 17 x to the fourth. So it has solutions over R and any QP, but not over Q. So this Minkowski-Hasse principle is very important and general principle, but only works in some restricted situations. For example, for quadratic forms, but not in general, not for general algebraic varieties, for higher degree equations. Yes? When this acquires a solution, yeah? How to find a solution in QP? Yeah, maybe starting from Hensel lemma or. Yeah, at least for if P it does work, yeah. Though it's not a? Mm-hmm. Okay, but now if we believe this Minkowski-Hasse principle, in fact, it's proved, say, in the famous book by Serre, Course in Arithmetic. If we believe this, then you can provide some explicit criterion for a quadratic form to have a non-trivial 0. So explicit local criteria for Q over QP to have a non-trivial 0. Well, so we introduce local invariance first a discriminant. And also the Hilbert symbol. Epsilon of Q. This is the product of all the matrix elements. So Q has matrix A, I, J. And the Hilbert symbols, shall I recall them, or is it well known? So in its turn, it has very many equivalent definitions. So it's equal to plus or minus 1. And say it's equal to 1. If A is a norm from QP extension by square root of B to QP, and well, maybe it's 1, and the equivalent property is that z squared minus a x squared minus b x squared equals 0 has a non-trivial solution. In QP, or else you can consider, pardon me? Oh, sorry, thank you. The quaternion algebra QP of Aij, modular relations I squared equals A, J squared equals B, and Ij anti-commute. This algebra is isomorphic to the matrix algebra. So there are two alternatives. It's either matrix algebra or SQ field, and they're distinguished by the value of Hilbert symbol. Okay, so the theorem says that Q of x equals 0 has a non-trivial solution. If and only if either rank of Q is 2 and the discriminant is -1, or rank of Q is 3, and the Hilbert symbol is well, Hilbert symbol of the Hilbert symbol of Q is the Hilbert symbol of -1 and negative discriminant. Or the rank of Q is 4, and the Hilbert symbol of Q is the Hilbert symbol of -1 and -1. And the discriminant of Q equals 1. Pardon me? Just the dimension of the space, Qn, yeah, n. Or the discriminant of Q is not equal to 1. So it's either discriminant is not 1 or discriminant is 1, but then the Hilbert symbol is equal to z. Yeah. And finally, if the rank is at least 5, then it always represents 0. Always has a non-trivial solution. If it has rank at least 5, then it always has a non-trivial solution. Always represents 0. Yeah. For rational forms, the only condition is that it's not positive or negative definite. If it's not definite in the Archimedean sense, then it always will have rational solution, non-trivial rational solution. Okay. Pardon me? Oh, yes. This is the main part of algebraic part of Serre book. Maybe let me just add one more word. Because this is for p-adic form, for local form. So you start from a global form, and then you're interested if it has non-trivial solutions. Then you localize it, go to p-adic completion, and then you compute something very robust. Yeah, just those invariants, Hilbert symbol and discriminant. And then you know for all the local fields, and by Minkowski-Hasse principle, you go back to the global problem, and you know the solution for a global problem. And one funny corollary is that there is a unique form of rank 4, not representing 0. Namely, this is the reduced norm of the quaternion field. Quaternion's Q field. HP. Or more explicitly, this is z squared minus ax squared minus by squared plus ab t squared for AB having Hilbert symbol -1. Okay. So it's clear that for quaternion field, its norm is a quadratic form, and it can have no zeros because it's skew field. I mean, H inverse is H divided by this norm. I don't know how to say it. Norm of H. So this norm never represents zero. Q equals norm. And
Что H-1 первый этаж делить на норму.
yes.
Но, кажется, не работает просто в обычных кватернионах.
Why?
Не понимаю.
Really?
Ну,
I think you have H times H conjugate is norm of H. Right? So H inverse is maybe right. Yes, thank you. Yes. I mean, there is a notion of equivalence of forms. I mean, the isometry of vector spaces. And up to this, there is just unique form of rank 4 not representing 0. Yeah, any rank 4 form not representing 0 is isometric to this one. And in particular, there is just one skew field of degree 4. Well, it's I don't know what follows from what, but this essentially is equivalent. The two things are essentially equivalent to each other.
потому что у тебя есть...
Because it's about having zeros. So here we discussed forms not having zeros, and here we discussed forms having zeros. Well, then I think I'm done. Thank you. Thank you. No.